Now we're going to get into the calculus behind e functions, e to the x or e to some function of x. So we're going to start with just how do you derive it? So kind of adding to our list of derivative rules. E is actually considered one of the easiest, if not the easiest thing to derive because it actually is its own derivative. It is the only function that the derivative models the slope of the original really unchanged. So the derivative of e to the x is e to the x. Now, obviously, you're not going to be given a whole bunch of e to the x. You're often going to be given something like e to the 5x or e to the 3x or e to the x squared. So your derivative in that case will be the original e to whatever power it was, and then the derivative of that exponent. So that's your du, or the derivative of the exponent. To be honest, I usually put that first. I usually put that in front of the e just because it looks a little bit better. But those are the two parts of your derivative. So I'm going to take you through really basic ones, and then I also want to take you through ones that combine rules from earlier in the course. So the first two are what I would consider your basic, your straightforward ones. So your derivative is the derivative of the exponent, which is just 2, times the original e function. So 2e to the 2x minus 1. With this one, your derivative, you might want to come off to the side to derive negative 3 over x. Think of it as negative 3x to the negative 1. So power out front, power 1 less. You get a derivative of 3 over x squared. And then times the original e, which you can either put it next to here. You can even move it to the bottom because it has a negative exponent. Or you could put it after the 3 over x squared. All of those would be considered correct. So here's a chain rule one. Now I'm going to try to mix rules here, talk about this new e derivative in conjunction with what you've already learned. It's also a really helpful way to review earlier topics. So this is a chain rule. So with your chain rule, it is power out front, power 1 less, and then derivative of what's inside, and here's where the new stuff comes in. The derivative of e to the 2x is going to be 2e to the 2x, and the derivative of e to the x is just e to the x. And while your answer is kind of long with a chain rule, I would not take the time to simplify that at all. If you have a natural log and e's mixed together, keep in mind the way that we derive a natural log is du over u, so the derivative of what you're taking the log of divided by the original. So the derivative of this is going to be 3 plus 4e to the 4x over the original 3x plus e to the 4x. These end up having very similar looking numerator and denominators. It's tempting to try to cancel on something, but nothing actually does. These two, my favorite two rules to do side by side. The fifth one is a product rule, and my sixth one is a quotient rule. I usually do those back to back purposely. So first times the derivative of the second, derivative of e to the 2x is 2e to the 2x, plus second times the derivative of the first, the derivative of x is just 1, and you can leave your answer like this. There's really not much simplifying you could do anyway. For my quotient rule, bottom times the derivative of the top, the derivative of e to the 3x is 3e to the 3x, minus the top times the derivative of the bottom. I'm going to put the derivative of the bottom first, all over the bottom squared. When I square e to the 3x, I get e to the 6x. There might be a little simplifying we can do here with the e's, but honestly, I would just leave it. Unless you had a multiple choice where they did go further, I would stop right here. We can have e's and trig put together. It's really just going to practice those trig derivative rules that it's always nice to review. Derivative of sine 2x is going to be 2 cosine 2x. So we derive the sine and we derive the angle. And then times the original e to the sine 2x. And wow, that looks kind of messy. There's nothing I can do to simplify that. The next one, this should be number 8. This is actually a case where log properties help us because I want to expand this, because by expanding it allows it to make it two simpler things to derive. So I'm going to expand with subtraction since we currently have a quotient. So I'm going to have the natural log of e to the x plus 6 minus a natural log of e to the x minus 3. So break up that division with subtraction. And then I'm going to do each term separately, du over u. So this is your u value, this is your u value. So the derivative over the original, so the derivative of e to the x plus 6 is just e to the x over e to the x plus 6 minus, same thing, derivative over original, and there is nothing you're going to do to simplify that. So log properties, trig rules, all of these things kind of come into play. I've got one left for this video. The one other thing we didn't talk about yet is implicit differentiation. We really haven't done implicit very recently, but you can see e's or natural logs or anything we've done to this point mix in with implicit. So with implicit, you're going to derive every term. You're going to use all your known rules, and anytime you derive a y term, you're going to have dy dx. So the derivative of 2e to the x is 2e to the x. No dy dx needed because it was an x term. Derivative of 4y is 4 dy dx. Derivative of 3e to the y is 3e to the y dy dx because the exponent is a y term. And the derivative of 10 is 0. So then the next step in implicit is to kind of rearrange things. Anything that doesn't have dy dx, I'm going to move that to the other side. And I'm going to factor out the dy dx with the terms that do have it. So I have a 4 plus 3e to the y on this side. And I'm going to move the 2e to the x, so it'll be a minus 2e to the x. And then divide. So my final answer, and our final answers for implicit are usually kind of messy in terms of both variables, is negative 2e to the x all over 4 plus 3e to the y. So that shows you how E shows up with all the different rules that we've learned. It gets a good practice of the old rules. I've got one video left, but this does the majority of the derivatives in this.